Right now, as you listen to this, a photon of light is arriving at Earth. It has been traveling for over 13 billion years. When it first set out on its journey, the universe was barely 300 million years old. There were no planets, no trees, no oceans, no one to see it leave. The galaxy that emitted that photon was small, hot, and furious with the energy of newborn stars, burning through hydrogen at a pace that would exhaust itself in a cosmic blink. And when that photon left home, the distance between it and where you are now sitting was a fraction of what it is today. But the universe had other plans. Space itself was stretching, expanding, pulling the origin point of that ancient photon further and further away, even as the light raced toward a destination that did not yet exist. And something happened to that photon along the way. Its wavelength, originally a fiery ultraviolet, was pulled and stretched by the expansion of space until it shifted through visible blue, through green, through yellow and red, all the way down into the infrared. By the time it finally reached our telescopes, that light was no longer visible to the human eye at all. It had been redshifted beyond recognition. That single word, redshift, contains within it one of the most staggering revelations in the history of human thought. It is the reason we know that galaxies are fleeing from one another. It is the reason we know the universe had a beginning. It is the thread that connects a sickly Austrian stonemason son, a quiet Indiana farm boy, a deaf woman working in a basement at Harvard, a Belgian priest, and a Missouri-born athlete who would shatter every assumption humanity had ever held about its place in the cosmos. This is the story of how we discovered that the universe is running away from itself, and how a simple change in the color of light rewrote everything we thought we knew about existence. To understand redshift, we first have to understand light. And to understand light, we have to go back to a time when nobody truly did. The language of light, how we read the stars. For most of human history, starlight was beautiful and mysterious, but ultimately mute. We could see the stars, chart their positions, and track their wanderings across the seasonal sky. But we could not know what they were made of. We could not know how far away they were. We could not know if they were moving toward us or away. The stars were lanterns hanging in the dark, and their secrets seemed permanently locked behind the sheer impossibility of distance. Then, in 1666, a 23-year-old Isaac Newton did something deceptively simple. He purchased a glass prism at a fair in Stourbridge, England, took it home to his darkened room in Cambridge, and held it in a beam of sunlight streaming through a small hole in his window shutters. What emerged on the far wall was not a single spot of white light, but a brilliant rainbow, a band of colors stretching from deep red through orange, yellow, green, blue, and violet. Newton called this band a spectrum, and with that one experiment, he proved that white light is not a single, pure thing. It is a mixture, a blend of every color, each corresponding to a different wavelength. Red light has a longer wavelength, violet light has a shorter wavelength, and everything else falls somewhere in between. Newton's prism was a revelation, but it was also a beginning. It would take more than a century for anyone to look more closely at that rainbow and notice something peculiar hiding inside it. In 1802, an English chemist named William Hyde Wollaston repeated Newton's experiment with better equipment. He narrowed the beam of sunlight entering his prism by passing it through a thin slit. And when he looked at the resulting spectrum, he saw something Newton had missed. There were dark lines interrupting the smooth flow of color. Thin, black gaps where certain wavelengths of light were simply absent, as if someone had taken a fine pen and drawn vertical stripes across the rainbow. Wollaston noted 7 of them, but he did not pursue the mystery further. He assumed they were simply the natural boundaries between colors. It fell to a young German craftsman to take the next step. Joseph von Fraunhofer was not a university professor. He was a lensmaker, an artisan who ground glass for telescopes and optical instruments with extraordinary precision. In 1814, while testing the quality of his lenses, Fraunhofer pointed his spectroscope at the sun and saw what Wollaston had seen, but in far greater detail. Where Wollaston had counted 7 dark lines, Fraunhofer meticulously mapped over 570 of them. He labeled the most prominent ones with letters of the alphabet, A through K, and these markings, known today as Fraunhofer lines, became the first detailed atlas of the solar spectrum. But Fraunhofer could not explain what caused them. He could see that specific wavelengths of sunlight were being absorbed by something. But what that something was remained a puzzle. He noticed that a bright orange line he saw in candle flames and alcohol burners appeared at exactly the same position as a dark line in the solar spectrum. A line he labeled D. The coincidence nagged at him, but he died young, at just 39, before he could solve the riddle. The answer came in 1859 in a university laboratory in Heidelberg, Germany, where 2 colleagues were about to revolutionize science. Gustav Kirchhoff was a physicist. Robert Bunsen was a chemist, the same Bunsen whose name adorns the burner that still sits in every high school chemistry lab. Together, they built a spectroscope, a device that could split the light from a flame into its component wavelengths with great precision, and what they discovered was electrifying. Every chemical element, when heated until it glows, produces its own unique pattern of bright lines at specific wavelengths. Sodium produces 2 brilliant yellow lines. Potassium produces lines in the red and violet. Lithium produces a striking crimson. These patterns were as individual as fingerprints. No 2 elements produced the same set of lines, and here was the key insight. When Kirchhoff placed a sodium flame between a bright light source and his spectroscope, the bright yellow lines of sodium did not simply add to the spectrum. Instead, they appeared as dark lines, absorbing exactly the same wavelengths they would normally emit. The bright lines and the dark lines were mirrors of each other. Emission and absorption were 2 sides of the same coin. Kirchhoff immediately understood the implications. The dark Fraunhofer lines in the solar spectrum were caused by elements in the sun's cooler outer atmosphere, absorbing specific wavelengths of light from the hotter interior below. By matching those dark absorption lines to the bright emission lines of known elements in the laboratory, Kirchhoff could determine what the sun was made of without ever leaving his desk. He identified iron, calcium, magnesium, sodium, nickel, and chromium in the solar atmosphere. For the first time in history, a human being has determined the chemical composition of a celestial object. This was spectroscopy, and it changed everything. The stars were no longer mute. They were speaking in a language of light, and now we could finally read it. Each element stamped its signature onto the light that passed through it, a cosmic barcode that could be decoded from any distance, whether the source was a candle flame in a Heidelberg laboratory or a star burning at the edge of the observable universe. And it was this language, this ability to read the specific wavelengths of starlight with precision, that would eventually lead to the most shocking discovery in the history of astronomy. Because if you know where a spectral line is supposed to be, and you see it somewhere else, something remarkable is happening. The light is being shifted, and the direction of that shift tells you whether the source is coming toward you or running away. But let us pause here for a moment, because the mechanics of how spectroscopy actually works deserve more attention. They are beautiful, and understanding them will make everything that follows far more vivid. When Kirchhoff and Bunsen heated sodium in their Heidelberg laboratory and saw two brilliant yellow lines appear in the spectroscope, they were witnessing a phenomenon that would not be fully explained for another 50 years, until the birth of quantum mechanics. But even without that deeper understanding, the observational principle was clear and reliable. Each element absorbs and emits light at precisely the same wavelengths, and no two elements share the same pattern. Why? The answer lies in the structure of the atom itself. Every atom consists of a nucleus surrounded by electrons that occupy specific energy levels. Like rungs on a ladder, an electron can jump from a lower rung to a higher one by absorbing a photon of light with exactly the right amount of energy. And it can fall back down by emitting a photon of that same energy. The energy of a photon is directly related to its wavelength. High-energy photons have short wavelengths toward the blue and ultraviolet end of the spectrum, while low-energy photons have long wavelengths toward the red and infrared. Because the energy levels of each element are unique, determined by the number of protons in its nucleus and the arrangement of its electrons, each element absorbs and emits at its own characteristic set of wavelengths. So when you pass white light through a cloud of hydrogen gas, the hydrogen atoms pluck out photons at very specific wavelengths, the Balmer series in the visible range, leaving dark lines in the spectrum. And when you heat that same hydrogen until it glows, it emits photons at those exact same wavelengths, producing bright lines against a dark background. The pattern is identical either way, like a lock and its key. Every element has its own key, and this key works across any distance. This is a remarkable thing. A hydrogen atom on Earth absorbs and emits at the same wavelengths as a hydrogen atom in a galaxy 3 billion light-years away. The laws of physics are the same everywhere. And so when astronomers capture the spectrum of a distant galaxy and see the familiar pattern of hydrogen lines, or calcium lines, or sodium lines, they can identify those elements with absolute certainty. But here is where redshift enters the picture. Suppose you know that the hydrogen alpha line, one of the most prominent emission lines of hydrogen, normally appears at a wavelength of 656.3 nanometers, a deep red color. You point your spectroscope at a distant galaxy and look for that line. You find it, but not where you expect. Instead of being at 656.3 nanometers, it appears at 719 nanometers, shifted toward the redder, longer wavelength end of the spectrum. The entire pattern of hydrogen lines is there, perfectly preserved, but shifted uniformly to longer wavelengths. This shift tells you two things. First, the galaxy contains hydrogen because the pattern matches. Second, the galaxy is moving away from you because the light has been stretched. And the amount of the shift tells you exactly how fast it is receding. In this example, the wavelength has increased by about 9.6%, corresponding to a recession velocity of roughly 29,000 kilometers per second. Astronomers quantify redshift with a simple number, denoted by the letter Z. If a spectral line's wavelength has been stretched by 50%, then z equals 0.5. If it has been doubled, z equals 1. The most distant galaxy currently confirmed, as of early 2026, has a redshift of about 14.4, meaning its light has been stretched to roughly 15 times its original wavelength. That photon started its journey as energetic ultraviolet radiation and arrived at the James Webb Space Telescope as faint infrared. This is the measurement at the heart of everything, every statement we make about the expansion of the universe, about the distances to faraway galaxies, about the age and fate of the cosmos, ultimately rests on our ability to measure redshift with precision. And it all begins with those dark lines in the solar spectrum that Fraunhofer mapped in 1814. The cosmic barcodes that Kirchhoff and Bunsen learned to read in 1859, shifted and stretched by the expansion of the universe that Slipher first measured in 1912, the Doppler effect. Waves in motion. The son of a stonemason really ought to have inherited the family business. The Dopplers had been cutting and shaping stone in Salzburg, Austria, since 1674, building a comfortable life and a fine house on the Hannibal Platz near the river. But young Christian Andreas Doppler, born on the 29th of November, 1803, was too frail for heavy labor. His body was slight, his health unreliable, and his lungs would trouble him for his entire short life. So instead of stone, he was given numbers. His parents sent him to study mathematics at the Polytechnic Institute in Vienna, and there his talent became apparent. Christian Doppler could see patterns in the abstract that eluded others, but talent did not guarantee success. After finishing his education, Doppler spent years drifting through temporary positions, tutoring, and applying for professorships that never materialized. He grew so discouraged that he very nearly emigrated to America, packing his belongings and making preparations for the voyage. Then, at the last moment, he received an offer to teach at a technical school in Prague, and he stayed. It was in Prague in 1842 that Doppler presented the idea that would make his name immortal. On the 25th of May, he read a paper to the Royal Bohemian Society of Sciences with the ornate title "On the Colored Light of Double Stars and Some Other Stars of the Heavens." The core idea was simple but powerful. Doppler proposed that the observed frequency of a wave depends on the relative motion between the source and the observer. Think of it this way. Imagine you are standing on the shore of a calm lake, and someone is throwing stones into the water at a steady rhythm, 1 stone per second. The ripples spread outward in concentric circles, and if the stone thrower is standing still, the ripples reach you at the same steady rhythm, 1 per second. But now imagine the stone thrower begins walking toward you while still tossing stones at the same rate. Each successive stone is thrown from a position slightly closer to you than the last, so the ripples bunch together. They arrive more frequently. The wavelength between each ripple is shorter. Conversely, if the stone thrower walks away from you, the ripples stretch apart. They arrive less frequently. The wavelength between each ripple is longer. Nothing has changed about the stones or the rhythm of throwing. What has changed is the relative motion between the source and the observer. Doppler realized that this exact principle applies to both sound and light. When an object producing sound moves toward you, the sound waves compress and the pitch rises. When it moves away, the waves stretch and the pitch drops. You experience this every time an ambulance passes you on the street. That distinctive shift from a high-pitched wail as it approaches to a lower-pitched moan as it recedes. The siren itself never changes. What changes is the wavelength of the sound reaching your ears. For light, the effect is the same, but expressed in color rather than pitch. Light from an object moving toward you gets compressed to shorter wavelengths, shifting toward the blue end of the spectrum. Light from an object moving away gets stretched to longer wavelengths, shifting toward the red. Blue shift means approach. Red shift means recession. Doppler himself was partly wrong about the specifics. He believed this effect could explain why certain binary stars appeared to differ in color, one red and one blue, as they orbited each other. The idea was appealing, but incorrect. The speeds involved were far too small to produce a visible color change to the naked eye. He also incorrectly treated light as a longitudinal wave, like sound, rather than a transverse wave, as had already been proposed by Augustin Jean Fresnel. But these errors did not invalidate the core principle. The Doppler effect was real, and it was testable. The first experimental confirmation came just 3 years later, in 1845, in one of the most delightful experiments in the history of physics. The Dutch meteorologist Christophorus Bijsballet hired a group of horn players and placed them on an open railroad flatcar. As a steam locomotive pulled the car past a group of trained musicians standing beside the tracks, both sets of musicians listened carefully and noted the pitch. The standing musicians heard the horn's pitch drop as the train passed, exactly as Doppler predicted. The effect was real for sound. It would take longer to confirm for light, because the speeds required to produce a detectable shift in the wavelength of light are enormously greater than the speed of a mid-19th century train. But by 1901, the Russian physicist Aristarch Belopolsky managed to verify the optical Doppler effect in a laboratory using a clever system of rotating mirrors. Christian Doppler himself would not live to see any of this. His lungs finally gave out, and he died in Venice on the 17th of March, 1853, at just 49 years old. But the principle he described would become one of the most important tools in the history of astronomy. Because if you could measure the spectral lines of a star and compare them to the same lines produced in a laboratory, any shift in their position would tell you how fast that star was moving toward or away from you. Kirchhoff and Bunsen had given astronomers the ability to read the chemical composition of the cosmos. Doppler gave them the ability to measure its motion. The stage was now set. The tools were in place. All that was needed was someone to point a telescope at the right patch of sky and discover something that would shatter every assumption about the nature of the universe. And that someone turned out to be a quiet, meticulous farm boy from the flatlands of Indiana. Mulberry, Indiana, is not the kind of place that produces revolutions in cosmology. In the 1870s, it was a small farming community surrounded by cornfields and gentle hills, the sort of town where a boy's future was measured in acres plowed and bushels harvested. But Vesto Melvin Slipher, born there on the 11th of November, 1875, had a different kind of ambition. He was quiet, careful, and deeply observant, qualities that would serve him well in the painstaking work of astronomy. Slipher studied mechanics and astronomy at Indiana University, earning his bachelor's degree in 1901. That same year, fresh out of college, he received an offer that would shape the rest of his life. Percival Lowell, the wealthy Bostonian astronomer who had founded the Lowell Observatory in Flagstaff Arizona, needed a young assistant to operate a newly purchased spectrograph, a device built by the renowned instrument maker, John Brashear. Slipher was hired, and he traveled west to the high desert plateau of northern Arizona, where the observatory sat atop a pine-covered hill called Mars Hill. Lowell had founded his observatory primarily to study Mars. He was convinced that the so-called canals visible on the Martian surface were evidence of an intelligent civilization, and he wanted to prove it. This was a controversial, and as it turned out, incorrect belief, but Lowell's enthusiasm and personal fortune kept the observatory running and well-equipped. Slipher's first assignment was practical: learn the spectrograph, calibrate it, and use it to measure the rotation periods of planets like Venus and Mars. Slipher took to the work with a patient diligence that impressed even the exacting Lowell. By 1909, however, Lowell's interests had begun to shift. The so-called spiral nebulae had captured the attention of astronomers worldwide. These were faint, fuzzy patches of light visible through telescopes, some of them displaying beautiful spiral structures. Nobody knew what they were. Some astronomers believed they were clouds of gas and dust within our own galaxy, perhaps even solar systems in the process of forming. Others suspected they might be something far more extraordinary, entire galaxies of stars, so distant that their individual suns blurred into a soft glow. Lowell asked Slipher to turn the spectrograph on these mysterious objects and measure their spectra. It was an enormously difficult task. The spiral nebulae were faint, far fainter than individual stars, and capturing enough light to produce a readable spectrum required exposing photographic plates for hours, sometimes across multiple nights. The 24-inch Clark refractor at Lowell Observatory was not the largest telescope in the world, but Slipher's skill with the spectrograph was extraordinary. He coaxed results out of the instrument that no one else had managed. On the 17th of September, 1912, Slipher obtained his first successful spectral measurement of a spiral nebula. His target was the Great Nebula in Andromeda, the largest and brightest of the spirals. After comparing multiple photographic plates taken over 4 nights, he calculated its radial velocity, the speed at which it was moving along the line of sight toward or away from Earth. The result was startling. The Andromeda Nebula was approaching the solar system at roughly 300 kilometers per second. This was an astonishing speed, approximately 3 times faster than any other celestial object whose velocity had been measured at that time. The light from Andromeda was blue-shifted, its spectral lines displaced toward shorter wavelengths, revealing that this enormous fuzzy patch was hurtling toward us at breathtaking speed. Slipher pressed on. Over the next 2 years, he measured the spectra of 14 more spiral nebulae, a task that consumed long, cold nights at the telescope and careful, tedious work in the measuring room. By August of 1914, he was ready to present his results to the American Astronomical Society. Of the 15 nebulae he had measured, 11 were redshifted, meaning they were moving away from us. Only 4, including Andromeda, were blue-shifted, and the speeds involved were enormous. Some of the nebulae receded at over 1,000 kilometers per second. When Slipher finished his presentation, something happened that was almost unheard of in the restrained world of academic astronomy. The audience rose to its feet and gave him a standing ovation. They understood, even if they could not yet articulate why, that these measurements were pointing towards something profound. The spiral nebulae were not drifting gently through space. They were racing away from us at velocities that defied explanation. By 1917, Slipher had expanded his catalog to 25 spiral nebulae. The ratio of redshifts to blueshifts had grown even more lopsided. 21 were receding, and only 4 were approaching. In that same year, Slipher made what would prove to be an astonishingly perceptive observation. He noted that the pattern of velocities suggested that our entire stellar system, the Milky Way itself, was moving through space at roughly 700 kilometers per second. He wrote that the high speeds of the nebulae and the asymmetry of their motion could be explained if the spiral nebulae were independent stellar systems located at great distances, a view that at the time was still deeply controversial. But Slipher was a cautious man. He did not attempt to plot his velocities against the distances of the nebulae, partly because reliable distances were not yet available, and partly because such a bold extrapolation was not in his nature. He measured, he recorded, and he published. The implications he left to others, and yet without those measurements, nothing that followed would have been possible. Slipher's redshifts were the raw material from which the expanding universe would be constructed. Every scientist who later plotted velocity against distance, from Lemaitre to Hubble, relied on the velocities that Slipher had patiently gathered in his small observatory on Mars Hill. It is one of the great injustices of scientific history that his name is not better known. Edwin Hubble, who would receive most of the credit for the discovery of the expanding universe, never measured a single galactic redshift himself. He used Slipher's. Vesto Slipher eventually became the director of Lowell Observatory, a post he held for nearly 3 decades. He oversaw the search for Planet X that led to Clyde Tombaugh's discovery of Pluto in 1930. He retired in 1952 and lived quietly in Flagstaff until his death in 1969 at the age of 93. A modest man to the end, he made little effort to publicize his own contributions. The standing ovation at the 1914 meeting remained the high-water mark of his public recognition during his lifetime. But the data was out there now, in the literature, waiting for someone to make sense of it, and making sense of it would require answering a question that had bedeviled astronomers for decades. What exactly were those spiral nebulae? Were they small, nearby objects within our own galaxy, or were they vast, distant island universes, each one a galaxy in its own right, separated from the Milky Way by millions of light-years of empty space? The answer would come, but not before one of the most famous showdowns in the history of science. Let us return, for a moment, to that August evening in 1914, when Vesto Slipher stood before the American Astronomical Society and presented his measurements of the radial velocities of 15 spiral nebulae. It is worth lingering on this scene, because it represents one of those rare, charged moments in the history of science when the people in the room sense, without fully understanding, that they are witnessing the beginning of something vast. Slipher was not a showman. He was a careful, methodical observer, the kind of scientist who distrusted grand claims and preferred to let the data speak for itself. His presentation would have been measured, precise, delivered in the flat cadences of a Midwestern farm boy who happened to have spent his life squinting through spectrographs. He would have shown his photographic plates, pointed out the displaced spectral lines, and reported his calculated velocities with the cautious hedging that was his professional trademark. And yet the audience, a gathering of astronomers who spent their lives debating arcane questions about stellar parallax and nebular classification, rose to their feet and applauded. Why? Because they understood, even if only intuitively, what those velocities meant. 1,000 kilometers per second, 1,800 kilometers per second. These were speeds that dwarfed anything previously measured in the cosmos. Stars within our galaxy move at velocities of tens or hundreds of kilometers per second. The spiral nebulae were moving 10 to 20 times faster. Whatever these objects were, they were not behaving like ordinary members of our galaxy. They were doing something else, something new, something that did not fit into any existing framework. The standing ovation was not just applause for good data. It was a recognition that the familiar cosmos had just been replaced by something larger, stranger, and more mysterious. The spiral nebulae were not what anyone thought they were. And the velocities Slipher had measured were the first physical evidence that the universe was in motion on a scale that nobody had imagined. It would take another 15 years for Hubble to connect those velocities to distances and establish the law of expansion. It would take another 17 years after that for the cosmic microwave background to confirm the Big Bang, and it would take another 33 years beyond that for dark energy to be discovered, revealing that the expansion is not just continuing, but accelerating. But it all started in that room, on that evening, with a quiet man from Indiana and his carefully measured spectral shifts. The universe was running away, and Slipher was the first to measure its footsteps. The great debate: what are the spiral nebulae? On the evening of April 26, 1920, a crowd gathered in the Baird Auditorium of the Smithsonian Museum of Natural History in Washington, D.C. The occasion was the annual meeting of the National Academy of Sciences, and the evening's entertainment was to be a special lecture, a debate between two astronomers on what was officially titled the scale of the universe. The topic might have sounded dry, but beneath the restrained language was a question of staggering importance. Is the Milky Way the entire universe, or is it merely one island in an ocean of galaxies? The idea of island universes was not new. The German philosopher Immanuel Kant had proposed it as far back as 1755, suggesting that the fuzzy nebulae visible through telescopes might be vast collections of stars, each one a separate Milky Way, so distant that their individual suns could not be resolved. But proposals and proof are different things. And by 1920, the question was still fiercely contested. In one corner stood Harlow Shapley, a 34-year-old astronomer from the Mount Wilson Observatory in California. Shapley was ambitious, brilliant, and nervous. He had recently done groundbreaking work using the distances of globular clusters to map the size and shape of the Milky Way, and his results were astonishing. He calculated that the galaxy was roughly 300,000 light-years across, far larger than anyone had previously imagined, and that the sun was not at the center, but rather off to one side. In Shapley's view, the Milky Way was so enormous that there was simply no need for anything beyond it. The spiral nebulae, he argued, were relatively small and close, perhaps gas clouds or forming solar systems within the outskirts of our own giant galaxy. In the other corner stood Heber Curtis, a 48-year-old astronomer from the Lick Observatory. Curtis was older, more experienced, and a far more polished public speaker, honed by years as a teacher of Greek and Latin before he turned to astronomy. Curtis believed the Milky Way was much smaller than Shapley claimed, perhaps only 30,000 light-years across, and that the spiral nebulae were indeed independent galaxies located at vast distances. He pointed to several pieces of evidence. The nebulae showed far more novae, or stellar explosions, than would be expected if they were mere patches within our galaxy. Many of them appeared to have dark bands across their middles, reminiscent of the dust lanes seen edge-on in our own Milky Way. And crucially, Slipher's velocity measurements showed that the nebulae were moving at speeds far too high to be gravitationally bound to the Milky Way. The debate itself was not the dramatic head-to-head clash that later histories would suggest. Each man gave a 40-minute talk. Shapley, who went first, read from a typed script and spent most of his time describing his work on the size of the galaxy, only briefly addressing the spiral nebulae toward the end. Curtis, the better speaker, used projected slides and presented his arguments with precision and flair. No transcript of the event exists, and contemporary accounts suggest that no clear winner was declared that evening. The audience, most of whom were not astronomers, left with a sense that the question remained open. But the debate crystallized the stakes. If Curtis was right and the nebulae were external galaxies, then the universe was unimaginably larger than anyone had supposed. If Shapley was right, then the Milky Way was everything. The answer would not come from rhetoric. It would come from a single photograph taken 3 years later, 1,000 miles to the west, on a mountaintop in Southern California. And the person who took that photograph would need one crucial tool: a method for measuring the distances to the spiral nebulae with something approaching certainty. That method already existed. It had been discovered more than a decade earlier by a woman whose name should be spoken in the same breath as Hubble and Einstein, but almost never is. In the early 1900s, the Harvard College Observatory was one of the foremost astronomical institutions in the world. But it had a peculiar labor arrangement. The observatory's director, Edward Charles Pickering, employed a team of women to perform the tedious but essential work of analyzing photographic plates, measuring the positions and brightnesses of thousands of stars. These women were called computers, a term that in that era referred to a person who computed, not a machine. They were paid about 25 to 50 cents an hour, significantly less than the male astronomers who designed the observations. They were not allowed to operate the telescopes. Many of them had college degrees, some from the very best schools, and yet they were confined to a basement room, hunched over glass plates with magnifying loops, recording data in meticulous handwriting. Among them was Henrietta Swan Leavitt. Born on the 4th of July, 1868, in Lancaster, Massachusetts, Leavitt had attended Oberlin College for 2 years and then transferred to the Society for the Collegiate Instruction of Women, which later became Radcliffe College. She developed an interest in astronomy during her senior year, and after graduating in 1892, volunteered as an unpaid research assistant at the Harvard Observatory. In 1902, she received a permanent staff appointment. Leavitt was assigned to study variable stars, a type of star whose brightness fluctuates over time in a regular, predictable pattern. She focused in particular on a class known as Cepheid variables, named after the prototype star Delta Cephei in the northern constellation Cepheus. Cepheids pulse, expanding and contracting like a slow-breathing lung. And as they do, their brightness rises and falls in a cycle that can last anywhere from a few days to several months. Pickering directed Leavitt to study photographs of the Small and Large Magellanic Clouds, two satellite galaxies of the Milky Way visible from the southern hemisphere. Using plates taken at Harvard's outpost in Arequipa, Peru, Leavitt cataloged 1,777 variable stars, but it was a subset of these, 25 Cepheid variables in the Small Magellanic Cloud, that held the key to everything. Because all the Cepheids in the Small Magellanic Cloud are approximately the same distance from Earth, their apparent brightness on the photographic plates was a direct reflection of their actual, intrinsic luminosity, and Leavitt noticed something remarkable. The brighter Cepheids had longer periods. A Cepheid that took 30 days to complete its cycle of brightening and dimming was intrinsically more luminous than one that took 3 days. The relationship was not vague or approximate. It was tight, consistent, and linear when graphed on logarithmic scales. In 1912, Leavitt published her findings. The paper was formally communicated by Pickering, who signed it, and the first sentence noted that it was prepared by Miss Leavitt. Even by the standards of the time, the attribution was remarkably grudging. Leavitt's discovery was presented almost as clerical work, but its implications were enormous. If you knew the period of a Cepheid's variation, you now knew its intrinsic brightness, and if you knew how bright a star actually was, you could compare that to how bright it appeared from Earth. The difference told you how far away it was, using the simple inverse square law of light. A candle at twice the distance appears 1/4 as bright. Leavitt had found a cosmic yardstick. Cepheid variables were standard candles, objects of known luminosity that could be used to measure distances across the universe. This was the missing piece. Without Leavitt's period luminosity relation, there would have been no way to determine whether the spiral nebulae were inside the Milky Way or beyond it. Without it, Edwin Hubble could never have proven the existence of other galaxies. Without it, the expanding universe would have remained invisible. Leavitt herself never received the recognition she deserved during her lifetime. She continued her work at Harvard, discovering over 2,400 variable stars and 4 novae. But she was never promoted beyond the head of stellar photometry and was never allowed to pursue her own independent research agenda. She died of cancer on the 12th of December, 1921, at the age of 53. 3 years later, the Swedish mathematician Gösta Mittag-Leffler wrote to her, expressing his intention to nominate her for the Nobel Prize in Physics. He had to be informed that she was already dead. Harlow Shapley, by then the director of the Harvard Observatory, replied to Mittag-Leffler's letter by suggesting that the real credit for the period luminosity relation belonged to him, Shapley. For his interpretation of Leavitt's findings, Shapley would eventually have a supercluster of galaxies named after him. Leavitt received a minor lunar crater, and much later, the posthumous honor of having her discovery referred to as Leavitt's Law. Edwin Hubble himself reportedly said that Leavitt deserved the Nobel Prize for her work, but by the time anyone was in a position to act on that sentiment, she was already gone. Science moved on, built on the foundations she had laid, while her name faded into the footnotes. It is a debt that can never be fully repaid, but her yardstick was now available. And the man who would use it to shatter the boundaries of the known universe was about to arrive at the most powerful telescope on Earth. Hubble at Mount Wilson, proof of other galaxies. Edwin Powell Hubble was, by any measure, an unusual astronomer. Born on the 20th of November, 1889, in Marshfield, Missouri, He grew up not as a bookish stargazer, but as an athlete. He played basketball, football, baseball, and track in high school. And at the University of Chicago, he took up boxing with enough skill that promoters reportedly tried to recruit him for a professional bout against the reigning heavyweight champion. He was tall, athletic, handsome, and charismatic, the last person you might expect to spend his nights shivering at the eyepiece of a telescope on a cold mountaintop. But Hubble was also brilliant. He earned his undergraduate degree in mathematics and astronomy from Chicago in 1910, then won a Rhodes Scholarship to study at the University of Oxford, where, at his father's insistence, he studied law rather than science. He returned to the United States, passed the bar exam in Kentucky, and practiced law briefly. But the pull of the stars was too strong. Within a year, he abandoned his legal career and returned to the University of Chicago to pursue a doctorate in astronomy. His studies were interrupted by World War I. Hubble volunteered for the Army, served as a major in the infantry, and was reportedly gassed and wounded at the Battle of the Meuse-Argonne, though the exact details of his wartime service remain murky. After the armistice, he spent a year at the University of Cambridge before finally accepting a position at the Mount Wilson Observatory in Pasadena, California, in 1919. Mount Wilson was a special place, perched at an elevation of 5,700 feet in the San Gabriel Mountains above Los Angeles. It housed the most powerful telescope in the world, the 100-inch Hooker reflector, completed in 1917. Its mirror, made of plate glass cast in Saint-Gobain, France, and ground to a precise parabolic curve, could gather more light than any instrument ever built. It was the perfect tool for resolving the faint, fuzzy light of the spiral nebulae into individual stars, if such stars existed. Hubble set to work. On the night of October 5, 1923, he aimed the Hooker telescope at the Great Spiral Nebula in Andromeda and began a long photographic exposure. When he developed the plate, he initially marked what he thought was a nova, a new star that had temporarily flared in brightness. But as he continued to observe the same region over subsequent nights, he realized the star was not a nova at all. Its brightness was changing in a slow, regular pattern. It was pulsating. It was a Cepheid variable. Hubble was so excited that he crossed out the letters N for nova on his photographic plate and scribbled VAR beside it with an exclamation point. He had found exactly the kind of star that Henrietta Leavitt's law could measure. And when he applied Leavitt's period luminosity relation to this Cepheid, the result was unambiguous. The star was far too distant to be inside the Milky Way. The Andromeda Nebula was not a nebula at all. It was a galaxy, a vast island of stars at least 900,000 light-years away, far beyond the boundaries of our own galaxy, no matter whose estimate of the Milky Way's size you used. Within a year, Hubble had identified 12 Cepheids in Andromeda and found similar variables in other spiral nebulae. Each measurement told the same story. These objects were not clouds of gas drifting within our galaxy. They were separate galaxies, each containing billions of stars, each separated from us by stupefying distances. The great debate was over. Curtis had been right about the island universes, though his estimate of the Milky Way's size was too small. Shapley had been right about the sun's eccentric position within the galaxy, but wrong about the nature of the spirals. And the universe had suddenly become a much, much larger place. When Harlow Shapley received a letter from Hubble describing the discovery, he reportedly turned to a colleague and said, "Here is the letter that has destroyed my universe." He was right, but from the ruins of the old universe, a new one was about to be born. One that was stranger, more beautiful, and more terrifying than anyone could have imagined. Hubble announced his findings at a meeting of the American Astronomical Society on the 1st of January, 1925. The paper was read in his absence, and it shared the prize for the best paper presented at the meeting. A short article about the result appeared in the New York Times on February 10th. And just like that, the boundaries of the cosmos exploded outward. The Milky Way was no longer everything. It was one galaxy among millions, possibly billions. Each one a vast congregation of stars spread across an ocean of space, so wide that the light from the nearest neighboring galaxy had taken over 2 million years to reach us. But Hubble was not finished. Having established the distances to the nearby galaxies, he began to wonder about a pattern that was lurking in the data, a pattern that Vesto Slipher's redshifts had hinted at, but that nobody had yet put together in a systematic way. The distant galaxies were not only far away, they were moving away from us, and the farther away they were, the faster they seemed to be going. The implications of this pattern would take several more years to crystallize, and they would require the contributions of a Belgian priest, a Russian mathematician, and one colossal mistake by Albert Einstein to fully appreciate the revolution that Hubble and Lemaitre ignited. It helps to understand just how deeply ingrained the idea of a static universe was in Western thought. For more than 2 millennia, from Aristotle through Newton and beyond, the consensus view was that the cosmos was eternal and unchanging. The stars might wheel across the sky in their nightly procession. The planets might wander among the constellations, but the universe itself, in its fundamental structure, was permanent. Newton himself had recognized a problem with this picture. In a famous exchange of letters with the theologian Richard Bentley in the 1692 and 93, Newton admitted that a finite collection of gravitating objects ought to collapse inward on itself. His solution was to imagine an infinite universe, with matter spread uniformly in every direction, so that the gravitational pulls from all sides would cancel out, and the whole system would remain in equilibrium. It was an elegant idea, but it was wrong. A perfectly uniform infinite distribution of matter is gravitationally unstable. The slightest perturbation would cause clumps to form and grow. Newton's static universe was a house of cards, but nobody knew how to build a better one. The problem became more acute in the 18th and 19th centuries, when astronomers began to realize just how vast the universe might be. The philosopher Heinrich Albers articulated a paradox that bears his name. If the universe is infinite and eternal, and if stars are distributed uniformly throughout it, then every line of sight from Earth should eventually terminate on the surface of a star. The entire sky should be as bright as the surface of the sun, day and night. The fact that the night sky is dark implies that something is wrong with one of those assumptions. Either the universe is not infinite, or it is not eternal, or the stars are not distributed uniformly, or something else is going on that reduces the amount of light reaching us. Albers' paradox was debated for decades, but no satisfying resolution emerged. The problem was that nobody was willing to consider the most radical solution, that the universe is not eternal, that it had a beginning, that it is changing over time. The philosophical commitment to an unchanging cosmos was so deep that even Einstein, the most creative physicist of the 20th century, could not bring himself to accept what his own equations were telling him. He preferred to introduce an artificial fudge factor rather than entertain the possibility that the universe was expanding. This is worth dwelling on because it illustrates something important about how science actually works. Scientists are not dispassionate logic machines who follow the evidence wherever it leads. They are human beings with preconceptions, biases, and philosophical commitments that can blind them to possibilities that lie outside their expectations. The discovery of the expanding universe was not delayed by a lack of data or a failure of instruments. It was delayed by a failure of imagination, a collective unwillingness to consider that the universe might not be what everyone assumed it was. When Friedman published his expanding universe solutions in 1922, Einstein dismissed them. When Lemaitre published his observational evidence in 1927, Einstein called his physics abominable. Even after Hubble's 1929 paper made the expansion undeniable, many physicists resisted. The steady-state theory, proposed in 1948 by Hoyle, Bondi, and Gould, offered an alternative in which the universe expanded. But matter was continuously created to fill the gaps, maintaining a constant average density forever, with no beginning and no end. It was an ingenious idea, and it held significant support among cosmologists for nearly 2 decades, until the discovery of the cosmic microwave background in 1965 rendered it untenable. The lesson is that great discoveries often require not just new data, but new ways of thinking. And sometimes, the hardest part of a scientific revolution is not finding the evidence, but convincing people to look at it with fresh eyes. In 1915, Albert Einstein published his general theory of relativity, a set of equations describing how matter and energy curve the fabric of space-time, and how that curvature in turn dictates how matter and energy move. It was a triumph of human intellect, arguably the most beautiful and profound scientific theory ever devised. And almost immediately, it presented Einstein with a problem he did not want to face. When Einstein applied his equations to the universe as a whole, they told him something disturbing. A universe filled with matter could not remain static. The mutual gravitational attraction of all the matter in the cosmos would cause it to collapse inward on itself, like a ball of dough falling under its own weight. The equations demanded a universe that was either expanding or contracting. But Einstein, like virtually every physicist of his time, believed the universe was eternal and unchanging. The stars and galaxies had always been there, roughly where they were now, and always would be. The idea of a universe with a beginning or an end, a universe that changed over time, seemed almost absurd, more theology than physics. So Einstein did something he would later deeply regret. He added an extra term to his equations, a kind of mathematical knob he could turn to counterbalance the force of gravity and hold the universe in a static state. He called it the cosmological constant, designated by the Greek letter lambda. With this term in place, the equations could describe a universe that was perfectly balanced, neither expanding nor contracting. A cosmic tightrope walk between the inward pull of gravity and the outward push of this mysterious new force. Einstein published his static model in 1917, and for about a decade, it was the standard picture. The universe was eternal, unchanging, and held in equilibrium by the cosmological constant, but the equations had other ideas. In 1922, a young Russian mathematician named Alexander Friedmann, working in Petrograd, took Einstein's field equations and examined what would happen if you dropped the assumption of a static universe. The answer was dramatic. Without the cosmological constant propping things up, the equations produced a range of dynamic solutions. The universe could be expanding, it could be contracting, it could even oscillate between expansion and contraction. Friedmann was primarily interested in mathematics, not physics. He did not attempt to connect his solutions to any astronomical observations, and his paper, published in a German physics journal, received little attention. Einstein himself read it, initially believed it contained an error, and said so publicly. He later retracted the objection, but still dismissed Friedmann's work as mathematically correct but physically irrelevant. Friedmann died of typhoid fever in 1925, at just 37, never knowing that his equations described the actual universe. Then came Georges Lemaitre, born on the 17th of July, 1894, in Charleroi, Belgium. Lemaitre was a man of two vocations. He had studied civil engineering before World War I interrupted his education, and he served with distinction as an artillery officer in the Belgian army, witnessing the first poison gas attack in history. After the war, he abandoned engineering for both physics and the priesthood. He was ordained as a Catholic priest in 1923, and in the same year, he traveled to Cambridge, England, to study with the eminent astrophysicist Arthur Eddington. Eddington was deeply impressed, later describing Lemaitre as a very brilliant student, wonderfully quick and clear-sighted, and of great mathematical ability. From Cambridge, Lemaitre went to the Massachusetts Institute of Technology, where he earned his doctorate. While in America, he became familiar with both Slipher's redshift measurements and the emerging distance estimates for the spiral nebulae. And in 1927, after returning to Belgium as a professor at the Catholic University of Leuven, he published a paper that should have changed the world. The paper appeared in French in the Annals of the Scientific Society of Brussels, a journal that was widely distributed but seldom read outside of Belgium. In it, Lemaitre derived a solution to Einstein's field equations that described a universe expanding over time. But unlike Friedmann, Lemaitre did not stop at mathematics. He combined his theoretical solution with the observational data, using Slipher's velocity measurements and the best available distance estimates, to show that the recession velocities of the galaxies were proportional to their distances. He even calculated a numerical value for the rate of expansion. In other words, Lemaitre derived both the theoretical framework and the observational evidence for an expanding universe, 2 full years before Edwin Hubble published his famous paper on the subject. The paper was almost entirely ignored. Part of the problem was the obscure journal. Part of it was the language barrier, and part of it was the sheer audacity of the claim. An expanding universe was a radical idea, and it came from a Belgian priest writing in French. The scientific establishment was not ready. In October of 1927, Lemaitre attended the Solvay Conference in Brussels, a prestigious gathering of the world's leading physicists. The main topic was quantum theory, and Lemaitre was not invited to the formal sessions. But during a break, he managed to catch Einstein's attention, and the two men took a stroll together in the Parc Leopold. Lemaitre explained his work. Einstein listened politely, acknowledged the mathematical competence, and then delivered a verdict that must have stung. "Your calculations are correct," Einstein said, "but your physics is abominable." Einstein still clung to his static universe. The idea that the cosmos was expanding was, in his view, simply unacceptable. But evidence was accumulating. By 1929, the static universe was becoming increasingly difficult to defend, and it was in that year that Edwin Hubble, working at Mount Wilson with his assistant Milton Humason, published the paper that would make the expanding universe impossible to deny. Hubble's law and the fleeing galaxies. Milton Humason was one of the most unlikely astronomers in history. He had never attended college. He had not even finished high school. As a teenager, he had worked as a mule driver on the pack trains that hauled construction materials up the mountain trails to Mount Wilson during the building of the observatory. He fell in love with the place and eventually took a job as a janitor, sweeping the floors of the dome that housed the great telescope. From janitor, he was promoted to night assistant, helping the astronomers with their observations, and there, his extraordinary talents became apparent. Humason had remarkably steady hands, superb eyesight, and an almost preternatural ability to guide the telescope during long photographic exposures, keeping the light of faint, distant galaxies precisely centered on the spectrographic slit for hours at a time. He became one of the finest observational astronomers of his generation without ever earning a degree. Hubble needed Humason because the next phase of his work required not just distance measurements, but spectral measurements, precise determinations of the redshifts of galaxies at ever greater distances. Many of the velocities for nearby galaxies were already available, courtesy of Vesto Slipher's patient decades of work at Lowell Observatory. But Hubble needed to push farther out, to galaxies so faint that even Slipher's skilled techniques could not reach them. Humason was the man for the job. Together, Hubble measured distances and Humason measured redshifts. In his landmark 1929 paper, A Relation Between Distance and Radial Velocity Among Extragalactic Nebulae, Hubble plotted the velocities of 46 galaxies against their estimated distances. The result was a roughly linear relationship. The farther away a galaxy was, the faster it was receding from us. A galaxy twice as far away was moving away twice as fast. 3 times as far, 3 times as fast. This relationship, which would become known as Hubble's law and later, officially renamed the Hubble-Lemaître law in 2018 to acknowledge Lemaitr's prior work, was a bombshell. It meant that the universe was expanding, not just parts of it, all of it. Every galaxy was moving away from every other galaxy, like raisins in a loaf of bread dough that is rising in the oven. The raisins themselves are not moving through the dough. The dough itself is expanding, carrying the raisins with it. And from the perspective of any single raisin, every other raisin appears to be moving away, with the most distant raisins receding the fastest. This is a crucial and often misunderstood point. The galaxies are not rockets firing through space. They are not fleeing from some central explosion point. Space itself is stretching. The fabric of the cosmos is expanding, and the galaxies are simply carried along with it, like boats on a swelling ocean. The redshift we observe in their light is not, strictly speaking, a Doppler shift caused by their motion through space. It is a cosmological redshift, caused by the stretching of light waves as they travel through expanding space. The distinction matters because it means there is no center to the expansion. From every point in the universe, every other point appears to be moving away. There is no edge, no boundary, no preferred location. The expansion is happening everywhere, all at once. Hubble's original estimate of the expansion rate was roughly 500 kilometers per second per megaparsec, meaning that for every additional megaparsec of distance, about 3.26 million light-years, a galaxy's recession velocity increased by 500 kilometers per second. This value, known as the Hubble constant, was dramatically too high, a consequence of errors in his distance measurements. His distances were roughly 7 times too small, partly because he did not know that there were 2 distinct types of Cepheid variables with different luminosity calibrations, and partly because he sometimes confused bright gas clouds with bright stars, but the proportional relationship was correct. The farther you looked, the faster things were running away. By 1931, Hubble and Humason had extended their measurements to galaxies receding at 20,000 kilometers per second, pushing the observable boundary of the universe to distances that staggered the imagination. The expansion was real, it was measurable, and it could not be ignored. When the implications of Hubble's data reached Einstein, the great physicist finally surrendered. He abandoned his cosmological constant, reportedly calling it the biggest blunder of his life. In 1931, Einstein traveled to Pasadena and visited Mount Wilson, where Hubble showed him the evidence firsthand. Einstein reportedly declared that the visit had changed his mind. The static universe was dead. The expanding universe was born. The balloon analogy. Understanding the expanding universe. One of the most persistent misconceptions about the expanding universe is the idea that the galaxies are flying apart like shrapnel from an explosion. In this picture, there is a center, a point from which everything was launched, and the galaxies are rocketing outward through pre-existing empty space. This is wrong, and it leads to a host of confusion. If the universe has a center, then we must be somewhere relative to that center. Are we near it? Far from it? Is there an edge? What is beyond the edge? The truth is stranger and more elegant. There is no center. There is no edge. Space itself is expanding, and the galaxies are not moving through it. They are being carried along with it. The most helpful way to visualize this is to imagine the surface of a balloon. Picture a balloon that has not yet been inflated. On its surface, draw a number of small dots with a marker. These dots represent galaxies. Now begin to inflate the balloon. As the rubber stretches, every dot moves away from every other dot. From the perspective of any single dot, all the other dots are receding. And the dots that are farthest away are receding the fastest, because there is more rubber between them, and more rubber means more stretching. Notice several important features of this analogy. First, no dot is at the center of the expansion. The expansion is happening everywhere on the surface simultaneously. Second, the dots are not moving across the surface of the balloon. They are stationary with respect to the rubber directly beneath them. It is the rubber itself that is stretching, carrying the dots along. Third, the surface of the balloon has no edge. If you are a two-dimensional creature living on that surface, you can walk in any direction forever and never reach a boundary. The surface is finite, but unbounded. The analogy is not perfect, of course. Our universe is three-dimensional, not two-dimensional, and we do not know for certain whether it is finite or infinite. But the core idea holds. The expansion of the universe is not an explosion. It is a stretching of the fabric of space itself. And the redshift we observe in the light of distant galaxies is not a Doppler shift caused by their motion through space. It is a cosmological redshift caused by the stretching of light waves as they travel through expanding space. This distinction matters enormously. A Doppler redshift would imply that galaxies are objects moving through a stationary backdrop. A cosmological redshift implies that the backdrop itself is changing, stretching, growing, carrying everything along with it. The latter is what the equations of general relativity describe, and it is what the observations confirm. Consider a photon of light emitted by a distant galaxy 1 billion years ago. When that photon set out on its journey, the galaxy was at a certain distance from us. But space has been expanding during the entire billion years that the photon has been traveling. The space between us and the galaxy has been stretching, and the photon itself, a wave traveling through that stretching space, has had its wavelength stretched along with it. By the time it reaches our telescope, its wavelength is longer than when it was emitted. It has been redshifted, not because the galaxy is moving through space, but because space has grown during the photon's journey. And this is why more distant galaxies have higher redshifts. Their light has been traveling through expanding space for a longer time, accumulating more stretching, arriving with wavelengths that have been pulled further toward the red. The relationship between distance and redshift is the relationship between the duration of the photon's journey and the total amount of cosmic expansion it has experienced along the way. This is Hubble's law. This is the heartbeat of the expanding universe. And it all shows up in the shifted spectral lines of distant galaxies, the same lines that Fraunhofer mapped, that Kirchhoff decoded, and that Slipher patiently measured on cold Arizona nights. Einstein's biggest blunder and its resurrection. The story of Einstein's cosmological constant is one of the most ironic episodes in the history of science. In 1917, Einstein had introduced lambda as a mathematical patch to prevent his equations from predicting something he did not believe was possible, a universe in motion. It was, in his view, an ugly addition, a fudge factor that marred the elegant simplicity of his field equations. As he later wrote, "Since I introduced this term, I have always had a bad conscience. I am unable to believe that such an ugly thing is actually realized in nature." When Hubble's observations confirmed that the universe was indeed expanding, Einstein felt vindicated in his discomfort. The cosmological constant had never been needed. His original equations, without the extra term, had been right all along. They predicted expansion. He should have trusted them. Instead, he had let his philosophical prejudice, his belief in a static universe, overrule mathematics. According to the physicist George Gamow, Einstein once described the cosmological constant as his biggest blunder. But history has a wicked sense of humor. For decades after Einstein abandoned it, the cosmological constant gathered dust. Most physicists set it to zero and moved on. The universe was expanding. Gravity was slowing that expansion down, and the only real question was whether the cosmos would expand forever, gradually decelerating but never quite stopping, or whether it would one day reverse course and collapse back on itself in a fiery implosion. Then, in 1998, everything changed again. Two independent teams of astronomers, the Supernova Cosmology Project led by Saul Perlmutter, and the High-Z Supernova Search Team led by Brian Schmidt and Adam Rees, were studying a particular type of stellar explosion called a Type 1a supernova. These supernovae occur when a white dwarf star in a binary system accumulates matter from a companion until it reaches a critical mass and detonates. Because the explosion always happens at roughly the same mass, the resulting blast always produces roughly the same luminosity. Type 1a supernovae are standard candles, just like Cepheids, but vastly brighter, visible across billions of light years. Both teams expected to find that the expansion of the universe was slowing down. Gravity, after all, pulls everything together. Over billions of years, the combined gravitational attraction of all the matter in the cosmos should be acting as a brake on the expansion, like friction, gradually slowing a spinning top. If the expansion was decelerating, distant supernovae would appear slightly brighter than their redshifts would suggest, because they would be a bit closer than expected. Instead, both teams found the opposite. The distant supernovae were dimmer than expected. They were farther away than they should have been. The expansion of the universe was not slowing down, it was speeding up. The cosmos was accelerating. This was perhaps the most shocking discovery in the history of cosmology. Something was pushing the universe apart, counteracting gravity, and getting stronger over time. The physicists dusted off Einstein's old cosmological constant and realized that it provided exactly the mathematical framework needed to describe this accelerating expansion. The ugly thing that Einstein had dismissed was, in fact, a real feature of the universe. It represents a form of energy inherent to empty space itself, a kind of vacuum energy that pushes space apart at an ever-increasing rate. Scientists called it dark energy, and it turned out to constitute roughly 68% of the total energy content of the universe. Perlmutter, Schmidt, and Rees shared the 2011 Nobel Prize in Physics for their discovery, and Einstein's biggest blunder became, in retrospect, one of his most prescient insights. He had introduced the cosmological constant for the wrong reason, to keep the universe static. But the concept itself was correct. There really was a force opposing gravity at the largest scales. He just didn't know what it was. Echoes of the beginning, the cosmic microwave background. If the universe is expanding, then it was smaller in the past. Wind the clock back far enough, and everything, every galaxy, every star, every atom was compressed into a single, incomprehensibly hot, incomprehensibly dense state. This was the Big Bang, not an explosion in space, but an explosion of space itself, the origin of time, matter, and energy. The idea was first proposed in its modern form by Georges Lemaitre in 1931. Having already established the theoretical and observational basis for the expanding universe, Lemaitre took the next logical step. If the cosmos was growing larger, then in the distant past, it must have been much smaller. He imagined the entire universe compressed into what he called a primeval atom, a single quantum of cosmic matter from which everything emerged. At the time, most physicists found the idea preposterous. Fred Hoyle, a prominent British astrophysicist, who favored a competing, steady-state theory in which the universe had no beginning and no end, mockingly referred to Lemaitre's idea as a Big Bang. The name stuck, even though Hoyle had intended it as an insult. In the late 1940s, the physicist George Gamow and his colleagues Ralph Alpher and Robert Herman made a specific, testable prediction based on the Big Bang model. If the early universe was extremely hot, then as it expanded and cooled, there should have been a moment, roughly 380,000 years after the beginning, when the temperature dropped enough for electrons to combine with protons and form neutral hydrogen atoms. Before this moment, the universe was an opaque fog of charged particles and photons. with light unable to travel freely because it was constantly being scattered by free electrons. After this moment, known as recombination, the universe suddenly became transparent. The photons that were released at that instant should still be detectable today, stretched by billions of years of cosmic expansion from their original fiery temperatures into cold microwave radiation, filling every corner of the sky with a faint, uniform glow. Alpha and Herman predicted this radiation would have a temperature of about 5 degrees above absolute zero. But the prediction was largely ignored. The technology to detect such faint microwaves did not yet exist, and the theoretical physics community was not paying much attention to cosmology. The prediction sat in the literature, gathering dust, much like Einstein's cosmological constant. Then, in 1964, two radio astronomers at Bell Telephone Laboratories in Holmdel, New Jersey, stumbled onto one of the greatest discoveries in the history of science entirely by accident. Arno Penzias and Robert Wilson were using a large, horn-shaped radio antenna that had been built for satellite communications. They were trying to calibrate the antenna for a radio astronomy project, and they kept encountering a persistent, low-level hiss of microwave noise that they could not explain. The noise came from every direction. It was the same intensity whether they pointed the antenna north, south, east, or west, day or night, summer or winter. It was not coming from New York City. It was not coming from the Milky Way. It seemed to be coming from everywhere. They checked every possible source of interference. They tightened connections, replaced cables, and tested equipment. They discovered that a pair of pigeons had nested inside the horn of the antenna and coated the interior with what Penzias delicately described as a white dielectric material. They trapped the pigeons, shipped them to a distant Bell Labs facility, cleaned out the droppings, and resumed their measurements. The pigeons flew back. They trapped them again. The noise persisted. Penzias and Wilson were baffled. They had eliminated every instrumental and terrestrial explanation they could think of, and the mysterious hiss remained, steady and uniform, at a temperature of about 3.5 degrees above absolute zero. Meanwhile, just 60 kilometers away at Princeton University, a team led by the physicist Robert Dicke was building a radio telescope, specifically designed to search for the very radiation that Penzias and Wilson had accidentally found. Dicke's colleague Jim Peebles had independently recalculated the prediction that Gamo's group had made decades earlier, and concluded that the Big Bang should have left behind a detectable microwave background. When Penzias and Wilson learned about the Princeton group's work through a mutual acquaintance, the penny dropped. The mysterious hiss was not interference. It was the afterglow of creation itself, the cooled remnant of the fireball that had birthed the universe 13.8 billion years ago. Two papers were published side by side in the Astrophysical Journal in 1965. Penzias and Wilson described their observations. Dicke and his colleagues provided the theoretical interpretation. The cosmic microwave background had been found, and with it, the Big Bang theory moved from speculative hypothesis to established science. Penzias and Wilson received the 1978 Nobel Prize in Physics for their discovery. Dicke's group, which had predicted the radiation and was on the verge of detecting it themselves, was passed over in a decision that remains controversial. Jim Peebles would eventually receive his own Nobel Prize in 2019 for his decades of theoretical work on the history of the universe. and the cosmic microwave background itself became one of the most important tools in all of cosmology. It is the most distant light we can ever see, emitted when the universe was just 380,000 years old. Its temperature, measured with exquisite precision by satellites like COBE, WMAP, and Planck, is 2.725 degrees above absolute zero. It is almost perfectly uniform across the entire sky, but not quite. Tiny fluctuations, differences of just 1 part in 100,000, map the seeds of all the structure we see in the universe today. The galaxies, the clusters, the vast filaments and voids that make up the cosmic web. The cosmic microwave background is, in a very real sense, a baby picture of the universe. And like any baby picture, it tells a story of what came before and what would follow. It is redshift taken to its ultimate extreme, light that was once brilliant, fiery, and white-hot, stretched by 13.8 billion years of cosmic expansion, until it glows faintly in the microwave band, invisible to our eyes but detectable by our instruments. A whisper from the dawn of time, the night sky as a time machine. There is a profound and beautiful consequence of the finite speed of light that most people encounter as a simple fact, but rarely stop to fully absorb. Light travels fast, roughly 300,000 kilometers per second, fast enough to circle the Earth 7.5 times in a single second. But the universe is so enormously vast that even at this tremendous speed, light from distant objects takes years, centuries, millions or billions of years to reach us. This means that when you look up at the night sky, you are not seeing the universe as it is. You are seeing it as it was. The light from the nearest star beyond our sun, Proxima Centauri, took about 42 years to reach your eyes. You are seeing that star as it existed 4 years ago. The light from the bright star Sirius has been traveling for about 8.5 years. The light from the center of our own Milky Way galaxy has been journeying for roughly 26,000 years. It left its source before humans had invented agriculture. And when you turn a telescope toward the Andromeda Galaxy, the nearest large galaxy to our own, the photons striking your detector departed about 2.5 million years ago, before the genus Homo had fully emerged on the African savanna. When the Hubble Space Telescope captures an image of a galaxy cluster billions of light years away, it is photographing structures as they appeared when the Earth did not yet exist. This is not merely a poetic observation. It is a practical tool of extraordinary power. Because looking far away means looking back in time, astronomers can use the depth of the cosmos as a kind of archive, a fossil record written in light. By observing galaxies at different distances, and therefore at different epochs of cosmic history, they can trace the evolution of the universe from its earliest moments to the present day. Close galaxies show us the recent past. Distant galaxies show us the ancient past. And the cosmic microwave background, the most distant light we can detect, shows us the universe as it was just 380,000 years after the Big Bang, before any stars or galaxies had formed. Redshift is the key that unlocks this time machine. When an astronomer measures the redshift of a galaxy, they are simultaneously measuring its distance and its age. A galaxy at redshift 1 is seen as it was roughly 8 billion years ago, when the universe was about 6 billion years old. A galaxy at redshift 3 is seen as it was about 11.5 billion years ago. A galaxy at redshift 10 is seen as it was when the universe was only about 500 million years old. and a galaxy at redshift 14, like the record-breaking objects found by the James Webb Space Telescope, is seen as it existed less than 300 million years after the beginning of everything. Each increment of redshift takes us deeper into the past and closer to the origin, and each galaxy we find at higher and higher redshifts teaches us something new about how the universe assembled itself, how the first stars ignited in clouds of primordial hydrogen, how those stars forged heavier elements in their cores and scattered them into space when they died, and how those enriched clouds collapsed again to form new generations of stars and planets. The history of the universe is not written in books. It is written in light, and redshift is the page number that tells us where to look. We live in a golden age of cosmological discovery, and redshift remains the key that unlocks the universe's secrets. When the James Webb Space Telescope launched on Christmas Day, 2021, and unfolded its golden mirror at the second Lagrange point, 1,000,000 miles from Earth, astronomers knew it would peer deeper into the cosmos than any instrument before it. Webb was designed to see in the infrared, precisely because the most distant objects in the universe have had their light stretched so severely by cosmic expansion that it has shifted entirely out of the visible spectrum and into the infrared. The results have been astonishing. Within the first 2 years of operation, Webb discovered galaxies at redshifts that shattered all previous records. The JADES program, the JWST Advanced Deep Extragalactic Survey, found hundreds of candidate galaxies from the first 650 million years after the Big Bang. Among them was a galaxy designated JADES GSC 14-0, confirmed at a redshift of about 14.3, meaning we see it as it existed less than 300 million years after the Big Bang. Its light has been traveling for over 13.4 billion years. And in early 2026, the record was broken yet again. A galaxy dubbed MZ14, confirmed at a redshift of 14.44, pushed the boundary back to roughly 280 million years after the beginning. These galaxies are not what astronomers expected. Before Webb launched, theoretical models predicted that the first galaxies would be tiny, dim, and rare. Instead, Webb has found them to be surprisingly bright, surprisingly massive, and surprisingly numerous. Some of them show evidence of chemical enrichment, elevated levels of elements like nitrogen and oxygen, which suggest massive stars formed and died within them far more quickly than standard models predict. The universe, it seems, got to work building structure faster than we thought possible. This mismatch between observation and theory is one of the most exciting developments in modern astrophysics. It does not mean the Big Bang model is wrong. The cosmic microwave background, the abundances of light elements forged in the first few minutes of cosmic history, and the large-scale structure of the universe all powerfully confirm the basic framework. But it does mean that our understanding of galaxy formation in the earliest epochs needs revision. The universe is telling us something new, and redshift is the language in which it speaks. There is also a puzzle lurking in the numbers. When astronomers measure the expansion rate of the universe using nearby objects, like Cepheid variables and Type 1a supernovae, a technique that traces the expansion of space in the relatively recent cosmic past, they get one value for the Hubble constant, about 73 kilometers per second per megaparsec. But when they measure the expansion rate using the cosmic microwave background, extrapolating forward from the conditions of the early universe, they get a different value, about 67.4. The disagreement between these two numbers, known as the Hubble tension, is now statistically significant, well beyond the level that can be explained by measurement errors. Nobody knows what is causing this discrepancy. It might be a systematic error in one or both sets of measurements. It might be a sign that the standard model of cosmology is incomplete. It might be telling us something new about dark energy, or about physics we have not yet discovered. The James Webb Space Telescope has confirmed the Cepheid-based measurements with extraordinary precision, ruling out many potential sources of error. The tension persists, and until it is resolved, the precise rate at which the universe is flying apart remains one of the biggest open questions in all of physics. What is not in question is the expansion itself. From Slipher's first redshifts in 1912 to Webb's infrared images of the cosmic dawn, a century of observation has painted a picture of breathtaking clarity. The universe began in a hot, dense state. It has been expanding ever since. That expansion stretched the ancient light, turning the fierce energies of the early cosmos into the gentle, invisible whisper of the microwave background. It is carrying the galaxies apart from one another at ever-increasing speeds, driven by a mysterious dark energy that we can measure but cannot explain. And if the expansion continues to accelerate, then the far future of the cosmos is one of increasing isolation. Galaxies beyond our local group will be carried beyond the observable horizon, their light redshifted to infinity, until they vanish from view entirely. 1 trillion years from now, if some civilization exists in the remnant of our galaxy, they will look out at the sky and see nothing but their own stars. The evidence that the universe once contained billions of galaxies will be gone, erased by expansion. They will have no way of knowing what we know now. But we do know. We know because of a glass prism held in a beam of sunlight in 1666, because a sickly Austrian mathematician noticed that waves change frequency when their source moves. Because a careful young man from Indiana spent decades in the Arizona night, coaxing faint spectra from fuzzy patches of light. Because a woman in a basement at Harvard paid pennies for her brilliance, found the pattern that turned pulsating stars into cosmic rulers. Because a Missouri athlete with a law degree pointed the world's biggest telescope at Andromeda and found the universe to be 1,000 times larger than anyone had dared to imagine. Because a Belgian priest trusted his equations more than the greatest physicist alive and dared to suggest that the cosmos had a beginning. Because 2 radio engineers in New Jersey cleaned pigeon droppings out of their antenna and accidentally heard the echo of creation. And because, right now, a golden mirror floating in space, 1 million miles from Earth, is catching photons that left their sources when the universe was barely old enough to have stars. Photons whose wavelengths have been stretched to 15 times their original length by the relentless expansion of space. Redshift is more than a measurement. It is a message. It is the universe telling us its own story, written in the stretched light of 100 billion galaxies, each one racing away from every other, each one a little island of warmth and complexity in an ever-expanding sea of cold, dark space. And the most remarkable thing about this story is that we, sitting on a small rocky planet orbiting an ordinary star in an unremarkable galaxy, figured it out. We read the message. We decoded the light. And we are still listening. What makes redshift such an extraordinary scientific tool is its universality. It applies to every type of electromagnetic radiation, from gamma rays to radio waves. It works across every distance, from nearby stars to the edge of the observable universe. It is not dependent on the type of object being observed. It works for stars, galaxies, quasars, and even the diffuse gas between galaxies, and it can be measured with remarkable precision, often to fractions of a percent. The first redshift surveys, in the early 20th century, measured the velocities of individual galaxies one at a time, a slow and painstaking process. But beginning in the 1980s and accelerating through the 21st century, astronomers developed techniques for measuring redshifts of thousands of galaxies simultaneously. Using spectrographs equipped with fiber optic cables that could capture light from hundreds of objects at once, the Sloan Digital Sky Survey, which began operations in 2000, mapped the three-dimensional distribution of over 1 million galaxies by measuring their redshifts. The resulting map revealed the large-scale structure of the universe in stunning detail. Vast filaments of galaxies connected by tendrils of dark matter, surrounding enormous voids where almost nothing exists. The pattern looks like a cosmic web, or perhaps like the interior of a sponge, with galaxies concentrated along the surfaces and emptiness in the holes. This structure was predicted by computer simulations of the expanding universe, and the agreement between prediction and observation is one of the great triumphs of modern cosmology. It is a testament to the power of redshift as a tool. By measuring the redshifts of millions of galaxies, astronomers have mapped the architecture of the cosmos on the largest scales accessible to observation. More recently, surveys like the Dark Energy Spectroscopic Instrument, or DESI, which began collecting data in 2021 from its perch on a 4-meter telescope in Arizona, are pushing these measurements to even greater precision and depth. DESI aims to measure the redshifts of over 30 million galaxies and quasars, creating the most detailed three-dimensional map of the universe ever assembled. By studying how the large-scale structure of the cosmos has evolved over time, DESI hopes to constrain the properties of dark energy and shed light on the Hubble tension. Each of these surveys relies on the same fundamental principle that Slipher discovered over a century ago: that the spectral lines of distant objects are shifted toward longer wavelengths, and that the magnitude of this shift is proportional to the distance and recession velocity of the object. The tools have become vastly more sophisticated. The datasets have grown from dozens of galaxies to millions, and the analysis techniques now employ machine learning and supercomputers. But at its core, the method is the same. You capture the light, you spread it into a spectrum, you measure the shift, and the universe tells you its story. To truly grasp the power of redshift, consider this thought experiment. Imagine you could somehow stand outside the universe and watch a beam of light as it travels from a distant source to your telescope. Let us follow several photons from different galaxies, each at a different redshift, and see what their journeys tell us about the history of the cosmos. Start close to home. The Andromeda Galaxy, our nearest large galactic neighbor, is blue-shifted. Its light is compressed, not stretched, because Andromeda is one of the few galaxies that is actually approaching us, drawn by the gravitational pull between our galaxy and its own. Within a few billion years, the Milky Way and Andromeda will collide and merge, forming a new, larger galaxy that some astronomers have nicknamed Milkomeda. The blue shift of Andromeda, measured by Slipher in 1912, was the very first radial velocity ever determined for a spiral nebula. It is a reminder that gravity, on relatively small scales, can override the expansion of the universe and pull things together, even as the cosmos on the largest scales tears them apart. Now look a little farther. A galaxy at redshift 0.01 is receding at about 3,000 kilometers per second, about 1% the speed of light. Its light has been traveling for roughly 140 million years. When it set out, dinosaurs had just disappeared from the Earth. The shift in its spectral lines is small, just 1%, but easily measurable with modern instruments. Go farther still. A galaxy at redshift 1, seen as it was about 8 billion years ago, is receding at a significant fraction of the speed of light. Its light has been stretched to twice its original wavelength, a spectral line that was emitted as ultraviolet radiation has arrived as visible light. This galaxy existed when the universe was less than half its current age, and it would look noticeably different from nearby galaxies, bluer, more chaotic, with a higher rate of star formation. Push deeper. A galaxy at redshift 5 existed when the universe was just over 1 billion years old. Its light has been stretched to 6 times its original wavelength. Much of the visible light it emitted has been shifted into the near-infrared, which is why the Hubble Space Telescope, with its infrared capabilities, was essential for studying galaxies at these distances, and why the James Webb Space Telescope, optimized for the infrared, can see even farther. And at redshift 14, the frontier of current observation, we are seeing light emitted when the universe was less than 300 million years old. The light has been stretched to 15 times its original wavelength. Everything that was visible when it left its source has been shifted deep into the infrared. The galaxy that emitted it was one of the very first to form, a tiny, hot, furious collection of newborn stars burning through their hydrogen fuel in the primordial darkness. Each step in redshift is a step back in time, a window into a younger, smaller, hotter universe. And the pattern of redshifts across all these galaxies, increasing with distance in the manner first described by Hubble, is the most direct evidence we have that the universe is expanding, that space itself is stretching, and that every galaxy is being carried away from every other galaxy on the swelling tide of cosmic growth. This is what Slipher saw in his displaced spectral lines. This is what Hubble plotted on his distance velocity graph. This is what Lemaitre predicted from Einstein's equations. And this is what the cosmic microwave background confirms with its faint, uniform, all-sky glow. The afterglow of the moment when the universe first became transparent, stretched by expansion from a brilliant white-hot fireball into a cold whisper of microwaves at 2.725 degrees above absolute zero. Redshift connects all of these discoveries into a single, coherent narrative. It is the golden thread that runs through a century of cosmological revelation, from a farm boy in Flagstaff to a golden mirror floating at the edge of the solar system, all of it telling the same story. The universe began. It is expanding, and the light of the cosmos carries the proof, written in the simple, eloquent language of shifted wavelengths. The precise value of the Hubble constant, the number that quantifies how fast the universe is expanding, has been a matter of intense scientific debate for nearly a century. Hubble's original estimate, 500 kilometers per second per megaparsec, was far too high. Over the following decades, improved distance measurements gradually brought the number down. By the 1960s, It was clear that the true value was somewhere between 50 and 100, but the range was frustratingly wide. Two camps of astronomers, led respectively by Alan Sandage and Gerard de Vaucouleurs, arrived at values that differed by a factor of 2, each insisting that the other was wrong. The situation improved dramatically with the launch of the Hubble Space Telescope in 1990. One of the telescope's primary missions, the Key Project, was dedicated to measuring the Hubble constant with unprecedented precision by observing Cepheid variables in galaxies out to about 60 million light-years and calibrating Type 1a supernovae at greater distances. The Key Project arrived at a value of 72 kilometers per second per megaparsec, with an uncertainty of about 10%. The long debate appeared to be settled. But then, the cosmic microwave background entered the picture. The Planck satellite, launched by the European Space Agency in 2009, measured the tiny temperature fluctuations in the microwave background with extraordinary precision. By analyzing the patterns of these fluctuations, cosmologists could infer the conditions of the early universe and calculate what the expansion rate should be today. Assuming the standard cosmological model is correct, Planck's answer was 67.4 kilometers per second per megaparsec, about 8% lower than the Cepheid-based measurement. At first, this discrepancy was attributed to measurement uncertainties, but as both methods have been refined and cross-checked, the gap has not closed. It has, if anything, grown more statistically significant. The James Webb Space Telescope has confirmed the Cepheid-based measurement with new observations that eliminate many potential sources of systematic error. The disagreement is now well above the 5 sigma threshold that physicists use to define a genuine discrepancy, not a fluke. This is the Hubble tension, and it is one of the most important unsolved problems in modern physics. If the measurements are correct, then something about our standard model of the universe is incomplete. Perhaps dark energy is not constant, but varies over time. Perhaps there is a form of matter or radiation in the early universe that we have not yet accounted for. Perhaps the laws of gravity need modification at cosmological scales. The possibilities are tantalizing, and none of them have been confirmed. What we can say is that the expansion of the universe, first detected as a faint redshift in the spectral lines of spiral nebulae over a century ago, remains a living, evolving field of discovery. Every new measurement refines our understanding. Every new observation pushes the boundary of the known. And the fundamental tool remains the same: the ability to read the shifted light of distant objects and translate that shift into speed, distance, and time. The fate of the universe itself depends on the answers. If dark energy remains constant, then the expansion will continue to accelerate forever. Galaxies beyond our local cluster will be carried past the cosmic horizon, their light redshifted to infinity, until they vanish from observation entirely. The observable universe will shrink, not because space is contracting, but because light from beyond a certain distance will never be able to reach us. The universe will become a lonely, cold, dark place, its story visible only to those who live early enough to see it. If dark energy weakens or reverses, other fates are possible. The expansion might slow and halt, followed by a contraction that brings everything back together in a final crunch. Or the universe might reach a state of maximum expansion and hold there, balanced on a knife edge between gravity and dark energy, unchanging for eternity. We do not know which of these futures awaits us, but we know how to find out. We build bigger telescopes. We measure more redshifts. We push deeper into the cosmic dark. And we listen to the message that the universe has been broadcasting since the beginning, encoded in every photon of stretched, reddened, ancient light. There is one final implication of the expanding universe that is rarely discussed, but deserves our attention, because it concerns the ultimate fate of knowledge itself. If the expansion of the universe continues to accelerate, as current observations suggest, then the observable universe will slowly shrink over the coming billions of years, not because the universe itself is getting smaller, far from it. It will continue to grow without limit, but because the expansion will carry distant galaxies beyond a kind of cosmic horizon. The light they emit will be stretched to such extreme wavelengths, redshifted so severely, that it will become undetectable. One by one, galaxies will fade from view, their photons stretched to infinite wavelength, their information lost. The first to vanish will be the most distant ones, the galaxies at the edge of the observable universe. Then, over hundreds of billions of years, closer and closer galaxies will follow, their light dimming and reddening until they wink out of observability entirely. Eventually, the only galaxies visible will be those gravitationally bound to our own local group: the Milky Way, Andromeda, and a few dozen smaller companions. Everything else will have been swept beyond the horizon by the accelerating expansion. In about 100 billion years, the cosmic microwave background itself will be stretched to wavelengths so long that it becomes effectively undetectable. The evidence for the Big Bang will have been erased. The redshifts of distant galaxies, the observational foundation of modern cosmology, will be gone. A civilization arising in that distant future would look out at the sky and see only its own local cluster of stars, surrounded by empty darkness. They would have no way of knowing that the universe once contained hundreds of billions of galaxies. They would have no reason to suspect that space is expanding. They might conclude, as our ancestors did, that the cosmos is static and eternal, a single island of stars in an unchanging void. This is a haunting thought. It suggests that the window of time during which the universe can be understood is finite. We happen to live in that window. We can see the cosmic microwave background. We can measure the redshifts of distant galaxies. We can piece together the story of the Big Bang and the expansion. But this ability is temporary, a gift of cosmic timing that will not last forever. The physicist Lawrence Krauss and the cosmologist Robert Schurer published a paper in 2007 exploring this scenario. They pointed out that virtually all of the evidence for the expanding universe, the redshift distance relation, the cosmic microwave background, the abundances of light elements, and the age estimates derived from distant objects would be inaccessible to observers in the far future. The universe would look completely different, and the conclusions drawn from observation would be completely wrong. This gives our present moment a special significance. Not because we are at the center of the universe, we are not, and there is no center. Not because we are uniquely important, we are not, and the universe does not care about us. But because we happen to exist at a time when the evidence is still visible, when the story can still be read, when the light from the earliest galaxies has not yet been stretched into invisibility. We are witnesses to a cosmic narrative that is slowly erasing itself. And that is perhaps the deepest lesson of redshift. It is not just a measurement. It is not just a tool for calculating distances or plotting expansion rates. It is a reminder that the universe is changing, that the information it offers us is finite and fleeting, and that the act of observation, of paying attention, of reading the light, is itself a precious and temporary privilege. Every photon that arrives at our telescopes from a distant galaxy is a message that has crossed billions of years of expanding space to reach us. It carries information about the conditions at the moment it was emitted, about the chemistry, temperature, and motion of its source, and about the stretching of space it experienced along the way. It is, in every literal sense, a message in a bottle, tossed into the cosmic ocean billions of years ago, arriving at our shore just in time for us to find it. One day, the bottles will stop coming. The ocean will have stretched too wide. The messages will be lost. But right now, today, they are still arriving, and we are still reading them. If you enjoyed this journey through the cosmos, please like and subscribe to the channel. Leave a comment and let us know what you think, or what topic you would like us to explore next. Thanks for watching, and we will see you next time.